Hello, Calc students. This is our first day talking about derivatives for real, as in for real, the way you're going to be expected to do them most of the time. Before we talk about the basic derivative rules, I want to talk about this notation thing because I'm going to write this both ways. And the issue is that there's two ways to write the derivative of a function, f, some function f. This is the way that we saw before. This is f prime of x. And you say it like f prime of x. And it's like the f with the little thing there, and that means the derivative of f of x. Okay? There's another way, which is to use this d over dx notation. And we're going to use this a lot, so you should know, you really have to know both of these. We're going to use both of them all the time. So this d over dx, this whole thing, this entire collection of symbols means the derivative with respect to x, and then of, like you'll put something in here, derivative with respect to x of f. This means the same thing as this. And this is often written like this, like df dx. This means the derivative of f with respect to x. It means that x is the variable in the problem. You can write it like df dx or d over dx of f or df dx. This is much more common to write it like this. And if sometimes the function is called y, and so it's often written like dy dx. This means the derivative of y with respect to x. But like the operator is d over dx. So it's like this means the derivative with respect to x of something. So for example, if I'm like, I have a function like f of x equals sine x. I want to know the derivative of this. You can say f prime of x. You can also say this. This means the derivative of, with respect to x of sine x. And this is a handy tool because it's like a thing I can write in front of things. So in theory, you could write this like this as well, like this and this and this all mean basically the same thing. It means the derivative, if f of x is sine x, this means the derivative of sine x, this means the derivative of sine x, this means the derivative of sine x. They all mean the derivative of sine x. And this is like I said before, you could write this way. It's not written this way very often. It's usually put the f on top of the fraction. But like this part right here is the, I would call it the operator. It's the thing that's actually, it's the thing you're doing to it. It's like if I have 10 squared, like 10 is the thing I'm squaring. Here it's like f is the thing I'm derivatizing. Derivating? It's hard to know what the right word is there. But so two ways to write this. F prime of x and d over dx. These and this. This is like basically Newton's way of writing it, and this is Leibniz's way of writing it. That's not really going to make that much of a difference that you know those people's names, but that's why there's two, because they both kind of invented calculus at the same time. So that's a notation thing, and I'm going to use both of them, and if you're confused about it, just ask me, because this is going to come up a lot, so let's try and hammer it out now. All right, that's a notation question. Basic derivative rules, okay? We could do this. I could show you how to do this with the limit definition, but I'm just going to tell you what the four simple rules are. The derivative of a constant, this is the Leibniz notation. This means the derivative of some constant c is 0, always. Doesn't matter what the constant is. The derivative of 2 is 0. The derivative of 10 is 0. The derivative of pi is 0. The derivative of negative a billion is 0. That's basically because the derivative tells you how a function is changing. And if the function is constant, it is by definition not changing. Its change is always 0. If I say the derivative with respect to x of pi squared, that's 0 because pi squared is always pi squared. There's like, it doesn't change at all. There's no x's in it that change. So it's always going to be equal to pi squared. The power rule is when we're going to use 1,000,000 times in tomorrow's or today's, depending when you're watching this. Today's in the classwork, and it says this: the derivative of a power of x to the n, where n is some integer, not integer, some like real number power of x. It could be a fraction, it could be a decimal, it could be a whole number. The derivative of a power of x is n x to the n minus 1. Basically, you move the power to the front and then subtract 1 from it. So I'll do one example here, but we're going to do a bunch of these later on. The derivative of x cubed is 3x squared. The 3 comes down to the front. That's why this came from. And you subtract 1 from the power and you get x squared. So we call this the power rule. The derivative of a power of x, bring the power to the front, subtract 1 from it every time. There's a sum and difference rule, which says if I have the derivative of a sum of two functions, I can just do the derivative of the first one and the derivative of the second one and add them together. It's like the derivative kind of distributes to the sum. It distributes to the addition sign. It also distributes to a minus sign, so I can just put a minus down here. It works whether it's f plus g or f minus g. It's always just take the derivative of each one individually and add them together. That's a g. This is important that you see this works for pluses and minuses, but it does not work for products and quotients. It works for adding and subtracting, but not multiplying and dividing. There's two rules, the product and quotient rule, which we're going to learn in the next class, which tell you for that. And the constant multiple rule, well, actually, let me do an example here. I'm not going to do an example yet. We'll do this in a minute. The derivative of a constant multiple of x, well, doesn't have to be x. Constant multiple of a function is the constant times the derivative of the function. Basically, you can move the constant to the front. This is going to happen, like if I know the derivative of x cubed is 3x squared, I know that because we saw it up here. That's like the power rule. Then the derivative of 4x cubed is going to be 12x squared. Because like the 4 just comes along for the ride. It just sits there. So I kind of ignore it. I do the derivative of x cubed, which is 3x squared. Then I multiply that by 4. So the way this would look using the constant multiple rule is that you would say this derivative is equal to 4 times the derivative of x cubed. Then you do this derivative, which is 3x squared, and that's 12x squared. I will never really expect you to do it this way. I'll expect you to do it this way. You just do the 3x squared. You can do 3 times 4 in your head probably. That's 12, and then x squared. So this is a constant multiple rule. It's just one of the basic ones that's basic enough that in 2 weeks you're not even going to be thinking about the fact that you're doing this. The same is true for both of these. You're just going to do them and not even remember that you're doing it that way. The derivative of a constant is 0. That's important. The power rule, very important. These rules are important, but they're kind of straightforward in the sense that you're not going to be thinking about it much later on. These two you got to remember. Okay. Here's another basic rule. It's pretty simple in the sense that if you have a function, if the function is e to the x, its derivative is e to the x. It's weird. It's another one of those reasons why e is such a special number. E is a magical number. And this is very weird, I think, because what it means is that when x is 0, this is the function f of x equals e to the x, and its derivative is also e to the x. So if I do f prime at 0, remember, this means it's the slope of the tangent to the graph of y equals e to the x for all x. So when x is 0, it's e to the 0, which is 1, which means it's right here, right? That's the tangent line at 0. And basically the height of the graph here, the height is equal to 1, and the slope of the tangent is equal to 1. And the fact that these are equal to 1, they're both equal to 1 is true for every value of x that exists for e to the x. It's very strange. I know you might be like, who cares? But I'm telling you that that is a very unusual thing. This is the only function for which that's true, that the derivative is the same as the height of the graph. Only true for e to the x. The reason I bring this one up now is because it's a pretty straightforward rule. If I have a function with an e to the x, its derivative is just e to the x. E is a magical number. Ooh, so spooky. All right. So here's a question, and it's like it kind of incorporates a couple different concepts. The first one is they give you a function. They say find the points on the graph where the tangent line is horizontal. So what you have to remember is that tangent line is horizontal. That's telling me something about the slope of the tangent line. This means the slope of the tangent line is equal to 0. A line with let me say that again. A horizontal line has a slope of 0. So if I say, where is the tangent line horizontal? This is asking me, where is the slope of the tangent equal to 0? Which is the same thing as saying, where is f prime of x equal to 0? Because the f prime of x is the slope of the tangent line to the function f at a value x. So the way we do that is we find f prime of x, and then we set it equal to 0 and solve for x. So I got to do f prime of x. So f of x is this function, x cubed minus 2x plus 4. So this is like, we're going to be using the constant multiple rule, the derivative of a constant, and the power rule, and the sum of difference rule. And as much as that seems like we're using 4 rules, I'm telling you that in like a week, you're going to think this is a very easy problem. So the derivative of x cubed we saw before, this is a power of x. So I pull the power down to the front. I leave the x there, and I subtract 1 from the power to get the new one. So 3 minus 1 is 2, so this is 3x squared. The derivative of negative 2x, there's 2 ways to think about this. I'll write it over here. So one way is to think of this as a constant multiple of x. It's just 2 times x. And the constant multiple rule says that this equals 2. The other way to think about it is to think about it as 2, this is x. X is just x to the first. So if I pull the 1 to the front, it's like 2 times 1, which is 2, times x. Then I subtract 1 from this power and I get 0. And x to the 0 is 1, because anything to the 0 is 1, so this just equals 2, which is the same thing we got here. I tend to think of it more like this. I'm like, the derivative of anything times x is just the anything. Sorry, let me say that again. The derivative of a constant times x is always equal to that constant. This was derivative of 10x, it'd be equal to 10. So the derivative of 30x, it'd be equal to 30. This is 2x, so it equals 2. So this is really minus 2. And then this is a 4. And the derivative of any constant is always 0. So what that means is that we're done now. The derivative of this thing is 3x squared minus 2 plus 0, which is just 3x squared minus 2. And the question was, what values of x make this equal to 0? Well, I can solve this equation. 3x squared minus 2 equals 0. 3x squared equals 2. X squared equals 2/3, which means x equals positive and negative square root of 2/3. So these are the 2 places on the graph where the slope, this is where f will have a horizontal tangent line. Because those are the places where the slope of the tangent line, which is this, is equal to 0. So you can stop here. In theory, it says find the points, which means you'd have to plug this back in to find the f of x's, but I just want to know what the x's are. Plugging that thing in back into here is going to give you some miserable answers for f of x. So we'll just leave it as plus or minus root 2/3. So a couple of big ideas in here. First big idea, slope of the tangent is the derivative, and a horizontal tangent means the slope of the tangent line is 0. That's what it means to be horizontal. It means if you have a 0 slope. The other big ideas were like taking derivatives of these powers of x. These are all basically powers of x, and there's some rules we use. The big one is the power rule. You move the 3 to the front, you subtract 1 from it, that gives you the derivative. Okay, last page. This should be pretty quick today. Find the derivative of the function. I put this one in these notes because students have had a lot of trouble with those in the past. So this one looks complicated. It looks like a quotient, but you don't have to do it that way. You can write it as 1 over t to the 1/2 minus 2t over t to the 1/2. I can split this up with the same denominator because there's only one thing on the bottom. And then 1 over t to the 1/2 is t to the negative 1/2. That's a rule of exponents. And this we got 2t to the first over t to the 1/2. And the rule of exponents I'm going to use here is the one that says when I divide two exponents, I divide two variables with this. How do you say this? When you divide two expressions, I divide two variables that have the same variable part, but different exponents, I subtract the exponents. So it's just t to the 1 minus 1/2, which is equal to 1/2. So this is the same thing as this. So now maybe it might be easier to find the derivative of this because it's just powers of x, or sorry, powers of t. So now I can say s prime of t is equal to, and now I use the power rule because this is just a power of the variable. So the power rule says I take the power that I have and I move it to the front. I leave the variable there. Now I subtract 1 from the power to get my new power. Negative 1/2 minus 1 is negative 3/2. Negative 1/2 minus 1 equals negative 3/2. That's just subtracting fractions from each other, right? I'm gonna do the same thing with the second power. Minus, and then I bring the power to the front, 1/2. And then I do t, and now I subtract 1 from this power. 1/2 minus 1 is negative 1/2. That's t to the negative 1/2. And now this problem is done. We've taken the derivative. You could like rewrite this thing with positive exponents, but there's really no need to do that. At least not today. And I'll tell you that, well, we'll talk about whether or not I want you to simplify things in the future, but the general answer to that, unless I specify, you do not have to simplify your answers. That's going to be a rule all through AP Calculus. You don't have to simplify your answers as long as they're right. So this is how you find the derivative of this. This one looks like a quotient, but you can really make it into powers of the variable, and those are very easy derivatives to take. So whenever you can do that, you probably should. And here's this last one is similar to the other ones, except this notation is a little weird. I'll tell you what this means. This means find the derivative of the function g, that's the one that's on top, with respect to t at t equals 1. This little bar here I call an evaluation bar, and this tells you the value that you're supposed to plug in at the end. So what this means is we're going to find the derivative of this function, then we're going to plug in t equals 1 at the end. The answer should be a number. This WRT means with respect to. It's just kind of shorthand. So the dg dt means the derivative of g with respect to t, and this little bar with the 1 means at the value t equals 1. This will usually say, I'm kind of not really sure why it doesn't here. This will usually say t equals 1. It'll tell you what the variable is here, even though you kind of already know it's t, it'll usually say that here. So we take the derivative first, so g prime of t. So this is the power of t, so I can use my power rule, which says I bring the power to the front. And then I subtract 1 from that power. Negative 3 minus 1 is negative 4. And then 2 root 2 is a constant. So its derivative is going to be 0. So I can just ignore it, plus 0. Then I have minus, and this is another power of t. Even though it's a fraction, it's still t raised to a number. So I bring the number to the front. That's another negative. So I have minus and negative, so I'm just going to make that up. Well, I'll write it like this. Negative 4/5 t, and then I got to subtract 1 from this. So just so you guys can see what I do, negative 4/5 minus 1 is negative 9/5. That's t to the negative 9/5. And this one, you probably ought to rewrite like this. Plus 4/5 t to the negative 9/5. And this is your answer. Oh, nope, I gotta plug in a 1. So this is the derivative. This is the first part. Find the derivative of g with respect to t. But now I gotta plug in the t equals 1. And that's kind of an easy one because 1 raised to any power is just 1. So if I go ahead and plug in t equals 1, I get negative 3 times 1 plus 4/5 times 1. And let's see, negative 3 is negative 15 over 5. So this is negative 11 over 5. And that's the answer. This is the last problem, so I'm going to just tell you guys what I mean when I say you don't have to simplify. And I mean it to the extent that if you got to this answer right here, you could stop there. You don't have to add these numbers together and get this one. This and this negative this are the same number. So if you're like, I don't really feel like adding this together because I might screw up the like adding a whole number to a fraction thing, then just stop right here. You can stop there. This answer is right. So is this answer. But this answer is right. And this is a calculus course, not an arithmetic course. And that's essentially the reason why I don't care if you simplify these answers. One caveat to that is that a multiple choice answer is always going to look like this one. So you actually kind of need to know how to do this because if there's a multiple choice question, the answers are going to look like fractions and not like the sum of two things. So there's like a kind of a warning there that, yeah, you can leave your answers like this if it's possible to do so, but there might be times where you actually have to figure out what this number is because your answer choices are going to be like A, B, C, and D, and none of them are going to look like this. So we can talk about that more in class if you guys want to, but that's the basic idea of simple derivative rules. So we'll talk about the bigger ones next. Bye.